Dear students, welcome. Today we shall start this multivariate calculus. We shall teach you vector calculus. In vector calculus, we shall discuss gradient, divergence, curve, line integral, surface integral, volume integral, Green's theorem, Stokes theorem, Gauss's divergence theorem, etc. Before that, I must give you some definitions, some preliminary things. Vector calculus. Vector calculus. Scalar field and vector fields. If to each point P, X, Y, Z of a region are in space, there corresponds a are in space, there corresponds a unique scalar Fp, then F is called a scalar point function. F is called a scalar point function, and we say that a scalar field F has been defined in if to each point P, X, Y, Z of a region are in space, there corresponds a unique scalar Fp, then F is called a scalar point function, and we say that a scalar field F has been defined in R. Vector fields. If to each point P, X, Y, Z of a region are in space, there corresponds a unique vector then F vector is called a vector point function. Then F vector is called a vector point function, and we say that a vector point function, a vector field, we say that a vector field F bar has been defined in R. If to each point these of a region are in space, there corresponds a unique vector, then F vector is called a vector point function, and we say that a vector field F vector has been defined in R. Now, I should give you some definition. Now, another definition. A vector function F vector of a scalar variable t is said to tend to a limit L vector. A vector function is of a scalar variability. F vector is a vector of the scalar variability. Is said to tend to a limit L vector when t tends to t0 if for every positive number epsilon, however small, if every positive number epsilon, however small, there corresponds a positive number delta. Such that f vector t minus L vector d is less than epsilon whenever 0 is less than t minus t naught is less than delta. Whenever 0 is less than delta. And we write limit as t tends to t naught f dash t equal to L vector. A vector function f vector t of a scalar variable t is said to tend to a limit, it is L vector, when t tends to t naught if for every positive number epsilon, every epsilon greater than 0, there exists a delta greater than 0 such that this is less than epsilon whenever this is less than delta. Now, we write this. Next, another definition. A vector function f bar t of a scalar variable t is said to be continuous for some t naught of t if number 1 f vector t naught is defined. F vector t naught is defined. Number 1 is this. Number 2, for every positive number, epsilon, however small, there corresponds a positive number delta such that positive number delta such that for every positive number epsilon, however small, such that it continuous, such that f T naught is less than epsilon whenever T minus T naught less than delta. Whenever T minus T naught is less than delta. Also, a function, a vector function f bar t is said to be continuous if it is continuous for all values of t for which it has been defined. For all values of t, in this case, a vector even scalar variable is said to be continuous. For some t naught of t. It is continuous for t is equal to t naught. A vector function here it is continuous for t is equal to t naught. It is means f vector t. F vector t is continuous for t equal to t naught. And a vector function is said to be continuous if it is continuous for all values of t equal to t naught, for which it has been defined. If it is continuous for all values. Next, another theorem. Thus, I am going to give you the statement of the theorem. A vector function f vector t is said to be continuous at t equal to t naught if and only if limit as t tends to t naught f vector t equal to f vector t naught. It is said to be continuous if and only if this is the theory. The statement of the theorem is this. Next, another theory. Statement of another theorem. What is the statement? Statement of another theory. If f vector t equal to suppose f1 t I cap plus f2 t j cap plus f3 t k cap, if f vector t equal to this one, then f vector t is continuous if and only if f1 t, f2 t and f3 t are continuous. F3 t are continuous. If and only if f1 t, f2 t, f3 t are continuous. This scalar functions are continuous, means the vector function will be also continuous. Now, next another theorem, the statement of the theorem. If f vector t equal to suppose f1 t I cap plus f2 t j cap plus f3 t k cap, and suppose the L vector is equal to L1 I cap plus L2 j cap plus L3 k cap, then limit as t tends to t naught f vector t equal to L vector if and only if, then this if and only if, or in other words you may say that then the necessary and sufficient condition for, then the necessary and sufficient condition, you may write in this way also, then the necessary and the sufficient condition, then the necessary and sufficient condition for limit as t tends to t naught f vector t equal to L vector r, limit t tends to t naught f1 t equal to L1 f1 t equal to L1, limit t tends to t naught f2 t equal to L2, and limit t tends to t naught f3 t, this is equal to L3. These are the cases. Now another theorem I am going to give. Another theorem, if f vector t, g vector t are two vector point functions of the scalar variable t, if f vector t and g vector t are two vector point functions of the scalar variable t, and if phi t be a scalar function of the scalar variable t, scalar function of the scalar variable t, then of the scalar function of the scalar variable t, then number one, limit as t tends to t naught f dash t plus g dash t, this is equal to limit as t tends to t naught f dash t plus limit as t tends to t naught g dash t. Similarly, if you put the negative sign here also, if it is plus, it is plus. If it is minus, it is minus. Just same thing as scalar calculus. Same thing as scalar. Number two. Limit as t tends to t naught f dash t dot g dash t, f dash t dot g dash t, this is equal to limit t tends to t naught f dash t dot limit t tends to t naught g dash t. This is dot. Obviously, this is a vector point function. It is also a vector point function. There must be either dot or cross. It is dot. Number 3. Limit as t tends to t naught, f dash t cross g dash t. Now the cross product is there. This is equal to limit as t tends to t naught, f dash t, this the cross product of limit as t tends to t naught, g dash t, g the vector function, g vector, like this. Number 4, limit t tends to t naught, phi t and f dash t. Here it is a scalar function, it is a vector function. Therefore, no need to write any dot or cross here. This will be equal to limit as t tends to t naught, phi t, into limit as t tends to t naught, the f dash t, like this. Number 5, limit t tends to t naught, f dash t will be equal to limit as t tends to t naught, f dash t, the modulus of this one. Right. Just you should remember all these things. And it will be applied in the later on. It will be applied later on. Let me now derivative of a vector function with respect to a scalar. Derivative of a vector function with respect to a scalar. Let R vector equal to F vector be a vector function of the scalar variable. Let R vector, this is a vector function of the scalar variable. We define R vector plus delta R equal to F vector t plus delta t. We define this. Now, delta R vector equal to R plus delta R minus R, which is equal to F vector t plus delta t minus, for R vector you may write yes, F vector t. Delta R vector equal to this. This means delta R vector by delta t equal to, you may write it as F vector t plus delta t minus F vector t divided by delta t. You may write like this. This means limit as delta t tends to 0, delta R vector by delta t equal to limit delta t tends to 0, F vector t plus delta t minus F vector t divided by delta t. If this limit exists, then we this limit exists, then we write it as dr vector by dt. It is denoted by, right? It just means it is denoted by this, and we say that see this as the differentiation of the derivative of r with respect to the scalar t. This limit exists. This is called it is denoted by dr vector by dt. It is the differentiation of the vector function with respect to a scalar. The derivative of r vector means the vector function. Derivative of vector function. You may write it as vector function. Derivative of vector function with respect to the scalar t. You may write like this. If this limit exists, it is denoted by this. Obviously, dr vector by dt is also a vector function of the scalar variable t. Obviously, dr vector by dt is a vector function of the scalar variable t. Of the vector function of the scalar variable t. If dr vector by dt is differentiable, then the derivative of this of dr by dt is, then the derivative of this is denoted by d2 r vector by dt, and is called the second derivative of r vector, and is called the second derivative of r. Also, if d2 r vector by dt square is also differentiable, then also if this is also differentiable, then the derivative of this means d2 r vector by dt square is denoted by d cube r vector by dt cube, and is called the third derivative of r, called the third derivative of r vector with respect to the scalar t. Sometimes we denote, you may write here, sometimes we denote dr vector by dt. It is denoted by r vector dot. R vector dot means dr vector by dt. And d2 r vector by dt square, it is denoted by r vector double dot. D cube r vector by dt cube, it is denoted by r vector triple dot, etc. We denote it just like this. Derivative of a vector function with respect to a scalar. Very simple. The means I am giving you the definitions. Now, one theory. I am going to give you one theory. If ABC A, B, C are three vector functions of the scalar variable P are three vector functions of the scalar variable P, and if phi be a scalar function of the same scalar variable T, then same scalar variable T, then we are going to prove number one, the d of A vector plus B vector. This is equal to just as the scalar dA vector, we will apply this one. dA vector by d A plus B vector, the differentiation of A plus B equal to sum of the differentiation of the two vectors with respect to the scalar. Number two, similarly minus sign you may write like this. Number two, d of A vector dot B vector. This is equal to, you will have to write A vector dB vector by dt plus dA vector by dt dot B vector. You may write like this. Number three, d of A vector cross B vector. This is equal to A vector cross dB vector by dt plus dA vector by dt cross B vector. Number two, d of phi A vector. This is equal to phi dA vector by dt plus d phi by dt A vector. You may write like this. Number 5, I am going to write number 5 here. Number 5, I am going to write number 5 here. Number 5, d of the scalar triple product, of these equal to dA dt this one. And number 6, I am going to write here number 6, d of A cross B cross C. This is equal to dA by dt cross B cross C plus A cross dB vector by dt cross C vector plus A cross B cross DC vector by dt. You may write like this. ABC are vector functions of the scalar variable T. Phi is a scalar function of the scalar variable T. It is applied on only in the number 4. ABC are applied in 1, 2, 3, 5 and 6. Phi is applied only in number 4. Then, just like scalar derivatives, d of A plus B equal to this one. Just let me try to prove one by one. Let me try to prove one by one. Number 1, d of A vector plus B vector. This can be written as limit as delta tends to 0 delta t a plus delta a plus b plus delta b minus a plus b. You may write like this. You may write like this. This is equal to, by definition, I have given you the definition. A vector, B vector will be cancelled. Delta A plus delta B divided by delta. This is equal to limit delta t tends to 0. Delta A vector by delta t vector plus delta B vector by delta t. This limit, you may write here delta t tends to 0, delta A vector by delta t plus again limit delta t tends to 0, delta B vector by delta t. From this is equal to dA vector by dt plus dB vector by dt. Thus d dt of this A vector plus B vector, we have proved that it is dA vector by dt plus dB vector by dt. Means the differentiation of the sum of two vectors, this is equal to the sum of the differentiation of the vectors. Differentiation of the sum of two vectors, this is equal to the sum of the differentiation of the vectors. Perhaps you have understood this. Number one, we have proved number one. Let me remove this one also. Now I am going to prove number two. Number two. This is number 6. Number 2 proof. D dt of A vector dot B vector. This is equal to, by definition, you may write delta t tends to 0, A vector plus delta A vector dot B vector plus delta B vector minus A vector dot B vector delta t. You may write like this. This is equal to limit as delta t tends to 0, just A vector dot B vector plus A vector dot delta B vector plus delta A vector dot B vector plus delta A vector dot delta B vector minus A vector dot B vector divided by delta t. Right. Just let me remove this one. Now, from this state, these two will be cancelled. This is equal to, from this state, equal to limit as delta t tends to 0, it is delta t A dot delta B vector plus delta A vector dot B vector plus delta A vector dot delta B vector. Right? This is equal to limit as delta t tends to 0. Delta t tends to 0. A vector dot delta B vector by delta t plus delta A vector by delta t dot B vector dot. It is dot plus delta A vector by delta t dot delta B vector. You may write like this. This is equal to limit as delta t tends to 0, A vector dot delta B vector by delta t plus limit as delta t tends to 0, delta A vector by delta t dot B vector plus limit delta t tends to 0, delta A vector by delta T dot delta B. This is equal to A vector dot, it is nothing but D vector by dt, limit of delta T tends to 0 equal to B, plus it is nothing but dA vector by dt dot B vector, plus it is nothing but dA vector by dt dot 0 vector, since delta B vector tends to 0 vector as delta T tends to 0. Delta B vector tends to 0 vector as, this is equal to A vector dot dB vector by dt plus dA vector by dt dot B vector. We have proved this one. D dt of A vector dot B vector equal to A vector dot dB vector by dt plus dA vector by dt dot B vector. Thus we have proved this one also. We have proved this one also. Just note it down. I am giving you the sums to note. Just I am sure that you have written. This has been proved. This has been proved. Now note one thing. We know that A vector dot B vector equal to B vector dot A vector. Because the dot product is commutative. Dot product is commutative. A vector dot B vector equal to B vector dot A vector. In this case, d dt of A vector dot B vector equal to A vector dot dB vector by dt plus dA vector by dt dot B vector. In place of this, you may write B vector dot dA vector by dt. You may write like this, because the dot product is commutative. A vector dot dB vector by dt plus B vector dot dA vector. You may write, in case of dot product, you may write like this. But in case of cross product, you cannot write like this, because A cross B equal to minus B cross A. Just remember this one. In this case, the in case of dA vector by dt dot B vector, you may write B vector dot dA vector by dt. Just but in number 3 you cannot write like this. You must write dA vector by dt first, because if you write B vector cross dA vector by dt, then A cross B equal to minus B cross A. Minus B cross A. Number 3. Just let me try to prove number 3. D dt of A vector cross B vector. Number 3. This is equal to limit as delta t tends to 0. Here it is delta t. Delta t tends to 0. It is delta t. You may write here delta A plus delta A cross B plus delta A minus A cross B by definition of. This is equal to, you may write limit as delta t tends to 0, A cross B plus A cross delta B plus delta A cross B plus delta A cross delta B minus A cross B. Minus A cross B. Divided by delta T. Divided by delta T. Right? You may write like this. Now, these two terms will be cancelled. A cross B will be cancelled. This is equal to limit as delta t tends to 0, A cross delta B plus delta A cross B plus delta A cross delta B divided by delta t. delta t. From this, I am going to write this. This is equal to limit delta t tends to 0 A cross delta b vector by delta t plus delta a vector by delta t cross b plus delta a vector by delta t cross delta b vector. You may write like this. From this step, you may write this step. This is equal to limit delta t tends to 0 A cross delta b vector by delta t plus limit delta t tends to 0 delta a vector by delta t cross b plus limit delta t tends to 0 delta a vector by delta t cross delta t. You may write like this. This is equal to a vector. Limit of this can be written as db vector by dt plus it can be written as dA vector by dt cross b vector plus dA vector by dt cross 0 vector because since you may write here since delta b vector tends to 0 vector, it is 0 vector as delta t tends to 0, as delta t tends to 0. This is equal to a vector cross db vector by dt plus dA vector by dt cross b vector. It is 0 vector. Thus, d dt of a cross b vector equal to a vector cross db vector by dt plus dA vector by dt cross b vector. Remember this, since a cross b equal to minus b cross a, since a cross b, this is equal to minus b cross a, you cannot intercept this one. You cannot intercept this. A cross db vector by dt plus, you cannot write b cross dA vector by dt. You must write dA vector by dt first. First write this, then write this. Okay? We have proved this one also. Thus number 3 has also been proved here. Now I am going to prove number 4. I am going to prove number 4. Note it down. I am giving you the chance to write. Perhaps you have written everything. Let me do this one. This one has also been proved. Now I am going to prove number 4. Prove number 4. Number 4. d dt of phi a vector, d dt of phi a vector, this is equal to limit delta t tends to 0, it is delta t phi plus delta phi. Phi is a scalar function, mind there, a plus delta a vector minus phi a vector. Phi vector. Phi is a scalar function. Mind that phi is a scalar function. This is equal to limit delta t tends to 0 phi a vector plus phi into delta a vector plus delta phi a vector plus delta phi delta a vector minus phi a vector divided by delta t. Now these two terms will be cancelled. Right? Now let me write. This is equal to limit delta t tends to 0 phi delta a vector plus delta phi a vector plus delta by delta A vector divided by delta t. This is equal to limit as delta t tends to 0 phi delta A vector by delta t plus delta phi by delta t A vector plus delta phi by delta t delta A vector. This is equal to limit delta t tends to 0 phi delta A vector by delta t plus limit delta t tends to 0 delta phi by delta t A vector plus limit delta t tends to 0 delta phi by delta t delta A vector. You may write that. This is equal to phi constant. Limit delta t tends to 0. Delta A by delta t is nothing but dA vector by dt plus it is d phi vector by dt, d phi not vector, d phi by dt A vector plus it is d phi by dt, it is 0 vector. Since delta A tends to 0 vector, it is 0 vector as delta t tends to 0, as delta t tends to 0. This is equal to phi dA vector by dt plus d phi by dt A vector, A vector, d phi by dt A vector. Thus d dt of phi A vector equal to phi dA vector by dt plus d phi by dt A vector. Just remember this. Just remember this. Right? Generally, phi is a scalar function. d phi by dt is also a scalar function. Generally, we write scalar function first, then we write the vector function. First write phi, then write dA vector by dt. d phi by dt first, then A vector. Generally we write in this way. We have proved 4 of the 6 theorems. Number 5, very important. The ABC vector within this bracket, what does it indicate? It indicates the scalar triple product of the vectors ABC. Scalar triple product of the vectors ABC. Scalar triple product of the vectors ABC. Now you number 5, d dt of ABC. It is nothing but the scalar triple product of the vectors d dt A vector cross. You may write like this. You may write in this way also. Just put this bracket. The cross product of the vector functions is a vector point function. B cross C is a vector function. A is a vector function. What does it mean? It is the differentiation of the dot product of two vectors. A vector is a vector. B cross C, cross product of two vector function, is also a vector function. Therefore, d dt of a vector function dot another vector function. We have already proved that d dt of a vector dot b vector equal to a vector dot db vector by dt plus dA vector by dt dot b vector. We have proved this one. Just we shall apply this. We shall apply this. This is equal to a vector dot d dt of b cross c plus dA vector by dt dot b cross c. dA vector by dt dot b cross c. since d dt of a vector dot b vector equal to a vector dot db vector by dt plus da vector by dt dot b vector. A vector dot b vector is equal to this. Also, we have proved this one. Also, b vector cross c vector is a vector. Vector point function is a vector. Therefore, it is a vector. It is also a vector. We have applied this. We have applied the number 2, theorem number 2. Now, you apply the theorem number 3 here. It is the differentiation of the cross product of two vectors by theorem number 3. We have just proved today. Dot. It is nothing but b vector cross dc vector by dt plus db vector by dt cross c. We have just proved it. Plus, just write it as it is. Right? We may write like this. This is equal to a vector dot product. It is a vector. It is also a vector. Dot product. A vector dot another vector plus another vector. Dot product is distributive. In vector algebra, you know it. The dot product is distributive. Therefore, you must write dc vector by dt. You must write like this. Plus a vector dot db vector by dt cross c vector. You must write this. You can write like this because dot product is distributive. It is of the form a vector dot b vector plus c vector. This is equal to a vector dot b vector plus a vector dot c vector. You may write like this. Therefore, you may write like this. Plus dA vector by dt dot b cross c. Let me remove this one. This is equal to, first write this one, dA vector by dt dot b cross c. First write this one plus next write this one. Next write a dot b cross dc vector by dt. This is equal. What is this? It is a scalar triple product a dot b cross c. Total 3 vectors are there. The dot product of 2 vectors. One vector is the cross product of 2 vectors. It is in total it is the dot product of 2 vectors. This is a vector, this is a vector. One vector is the cross product of 2 vectors. It is a scalar triple product. Therefore, we write the scalar triple product like this, BC. It is also a scalar triple product, A B vector by dt, C, scalar triple product of this, plus A B DC vector by dt, scalar triple product of this. Therefore, you see here, we have proved this one. Thus, proved. Thus, from this, left hand side. Thus, d dt of ABC, the scalar triple product of this equal to dA vector by dt BC plus A dB vector by dt C plus A B DC vector by dt. DC vector by dt. Thus, we have proved number 5 also. We have proved number 5 also. Perhaps you you have enjoyed this one. Number 6. Now I am going to prove number 6. Last one. I am going to prove number 6. The last one. Let me prove number 6. The last one. 6. D দ্বিতীয় A vector cross B cross C. You are going to prove. You see, B cross C, it is again a vector. It is a vector. Cross product of two vectors. This is this vector cross this vector. Because B cross C is again a vector function. We have proved in number C. I am going to apply number 3. It is nothing but A vector cross D দ্বিতীয় B cross C plus dA vector by dt cross B cross C. B cross C. Since D দ্বিতীয় we have proved A cross B equal to, in number 3, A cross dB vector by dt. We have applied this one, dA vector by dt cross B. We have applied this one also B cross C is a vector. That is why we can apply this. A cross this, that is why we can apply this one. Right? Now, again apply this here. D দ্বিতীয় B cross C. Again apply this. This is equal to A vector cross B cross DC vector by dt plus dB vector by dt cross C. Again apply this. Plus dA vector by dt cross B cross C. This is equal to, thus it is a vector. Vector product, it is a cross product, it's commutative. Thus you may write like this. You may write like this. This is equal to, first write this one, dA vector by dt B cross C, plus then write this one, A cross dB vector by dt cross C, and last write this one, A cross DC vector by dt. Very easy. Just we have applied theorem number 3 here. Perhaps you have enjoyed this one. dA vector by dt, yes. We have proved this one. All the theorems have been proved also. Just you should remember also, and you should prove it. You can prove it. Now I am going to give you one definition, which is called the constant vector. What do you mean by constant vector? Constant vector means magnitude constant, also the direction also constant. Constant vector means vector function. This can also be applied. Magnitude constant should and direction both are constants. Constant vector means magnitude constant and the direction constant. Then it is called a constant vector. Let R vector be a constant vector function. Let R vector be a constant vector function of the scalar variable t. Let the R vector be a constant vector of the scalar variable t. Then let R vector is equal to C vector. C vector is a constant vector. Constant vector. C vector is a constant vector. Therefore, R vector plus delta R vector, it will be again C vector. It will be again C vector. Thus, delta R vector equal to R vector plus delta R vector minus R vector. You may write like this. This is equal to, for this, you may write C minus C vector. This means delta R vector by delta t equal to, you may write C vector minus C vector divided by delta t. Divided by delta t. This means limit as delta t tends to 0. Delta R vector by delta t equal to 0 vector divided by delta t equal to 0 vector. This means dr vector by dt equal to 0 vector. Therefore, the differentiation of a constant vector is 0. Therefore, the derivative of a constant vector, derivative of a constant vector. Therefore, the derivative of a constant vector is a 0 vector. Derivative of a constant vector is a 0 vector. Differentiation of a constant vector is constant, derivative is constant. Now, right. Let R vector equal to x I cap plus y j cap plus z k cap. Here x, y, z are scalars and I cap, j cap, k cap are constant vectors. Are constant vectors, right? X, y, z are scalar and I cap, j cap, k cap are constant vectors. Now, therefore, dr vector by dt equal to, you may write d dt of x I cap plus y j cap plus z k cap. This is equal to d dt of x I cap plus d dt of y j cap plus d dt of z k cap. You may write like this. You may write like this. This is equal to x d I cap by dt plus dx by dt I cap plus y d j cap by dt plus dy by dt j cap plus z d k cap by dt plus dz by dt k cap. We have applied the theorem number 4 here. we have applied the theorem number 4 here. Since d dt of phi a vector, phi is a scalar, a vector is a vector. In this case, phi dA vector by dt plus d phi by dt a vector. We have applied this. Phi is a scalar and a is a vector. Here phi is a scalar, a is a vector. And a vector is a vector. We have applied number 4. We have applied number 4 here. We have applied number 4 here. Now I am going to write here also. Here. You may write here. This is equal to from this. Also, the constant vector, differentiation of a constant vector is equal to 0. Therefore, x 0 vector plus gx by dt I cap plus y 0 vector plus dy by dt z cap plus z 0 vector plus dz by dt k cap. Since I cap, j cap, k cap are constant vectors and derivative of a constant vector is 0. Of a constant vector is 0. 0 or 0 vector. Derivative of a constant vector is a 0 vector. From this you may write this is equal to dx dt I cap plus dy dt z cap plus dz dt k cap. You may write like this. You may write like this. Thus. If R vector equal to x I cap plus y j cap plus z k cap, then dr bar by dt equal to dx dt I cap plus dy dt z cap plus dz by dt k cap. We have proved this one. We have proved this one. Here vector by dt equal to dx dt I cap plus dy by dt z cap plus dz by dt k cap. We have proved this one. Perhaps you have enjoyed this. Try to remember all these things. All things are important. Mind that. All things are important. All things that we have given are important, which will be applied in the next chapters. You should simply know the derivatives of a scalar triple product. A vector, B vector, C vector. What is the differentiation of a scalar triple product? You simply know it. You simply know that if x vector is equal to this, x I cap plus y z cap plus z k cap, then the differentiation of dr bar by dt is equal to dx by dt I cap plus dy by dt z cap plus dz by dt k cap. Like this. If d dt of a vector dot b vector equal to, you should know that it is equal to a vector dot d vector by dt plus dA vector by dt dot d vector. In this case, since scalar product is commutative, then dA vector by dt and b vector can be interchanged. You may write b vector dot dA vector by dt. But in case of cross product, you cannot write like this. You cannot write like this. Such things just and try to understand it, and you will be able to understand it. I am very sure about it. In the next class, we shall meet again. Thanks for attending the class. Thank you very much.